So I'll be talking about smallest quantum codes for amplitude damping noise. Just a disclaimer that many of the introductory slides might be repetitive for many of us because earlier talks by Professor Prabha and Debjyoti. So I'll go through them quickly. If you have any question, you can stop me and ask questions. And before I move, I'd like to acknowledge Aditya. He's from University of Cambridge, and my guide, Professor Prabha Mandyam. So, as we all know, that the biggest challenge in building a quantum computer, scalable quantum computer to achieve quantum supremacy is noise. So that's why we need quantum error correction. If we just quote Preskill, so quantum error correction is our basis for thinking quantum computers are scalable to large devices solving hard problems. So in a nutshell, that we need quantum error correction to protect quantum information from this decoherence or noise. So what is noise? So for example, if you have a system and there is an environment, initially they are not entangled. And when we do when they interact through a joint unitary. And as we don't have control over the environment, we just trace out, and what remains is, we call this is a non-unitary evolution. So we call it as a quantum channel. And these are realized by operator sum representations, and these EKs are known as the Krauss operators. And we call this epsilon as a quantum channel. So there are many quantum channels. For example, there are bit flip, phase flip, depolarization. So these are little artificially made, but today I'll be talking about some noise model which is known as the amplitude damping. So this is naturally motivated, and this occurs naturally in many quantum hardwares, for example, the superconducting qubits. And when the system and the environment interacts under the Jaynes-Cummins interaction, this Hamiltonian, so what happens that the population from one state comes down to 0. So there is a probability that with probability gamma, it just like some photon or some population may get annihilated. And so this is related to the T1 time, T1 relaxation time, this formula. So gamma is called the damping strength. And if you look at the Krauss operator representation, so you can see there are two Krauss operators, A0 and A1. So A0 is basically, if the state is in 0 state, it will not do anything. And if it is in 1 state, with probability 1 minus gamma, it will remain in 1. But with probability gamma, the state will come from 1 to 0. So if you just break down, as you know, the Pauli's are, if some code can correct all the single Pauli error, that it also can correct this amplitude damping noise, because they are just combinations of Pauli's. So you can break down like this. So a general purpose code designed for only depolarization noise or Pauli noise can correct this, but there is some abuse of resources, because you are correcting sigma x, sigma y, sigma z separately. But we don't need that. We can see that there is, if you can correct sigma z here, and if you don't need to correct sigma x and sigma y separately, but you need to correct sigma x plus I sigma y. So we can just use this information to build quantum error correction code with fewer resources. So just an introduction and notation for quantum error correcting codes. So a quantum code is represented by nkq. So we say that k qubits are encoded into n qubits, where each qubit has q levels. And there are 3 blocks for error correction. First, we encode the system, like we encode the system in a subspace of a larger Hilbert space, and then noise acts on it, and then we do syndrome extraction, which is error detection, and then we apply recovery to correct. So there is this quantum error correction condition, which is popularly known as the Nil-Laflamme condition. So here is the equation, but I'll just like to present it through the diagram. So this is a full Hilbert space, and you have encoded your system into this subspace of this larger Hilbert space. So there are different errors. These are the Krauss operators of a channel epsilon. So different channels, different errors will take your code space to some orthogonal subspaces. So if this condition, this is the algebraic condition, if this condition is satisfied, then there exists a recovery channel R, such that this R conjugation with epsilon on rho will give you rho back, given that rho belongs to this code space. And so noise adapted quantum error correction, I have said that like if we know about the noise, then you can tailor your code for that particular noise and save on resources. Yeah, so for example, we need at least 5 qubits to protect a single qubit from depolarization noise. But if the noise is amplitude damping, we know that, then it is possible to achieve the similar performance, even better performance with 4 qubits. And these 4 qubit codes are explicitly mentioned in Prabha ma'am's talk or Dev Jyoti's talk. So now we ask the question, can we do better than 4? Can we go below 4? And the answer is yes, but we have to move out of the usual quantum error correction framework. So we propose a new approach for quantum error correction. So you have a code space, which is a span of these code words. So we are not now dividing the error Krauss operators in different groups, different sets. So each error set consists some eta A, so eta A Krauss operators, and that will take your code words to an orthogonal subspace. So this is, and each of these error subspaces should be orthogonal to each other. So this is the theorem. So consider a NQ code with logical state IL, and if we decompose the error channel like this epsilon with EAM. So if this condition is satisfied, then there exists a probabilistic recovery. So as we move out of the Neal-Laflamme framework, the recovery is not deterministic now. The recovery is probabilistic, which can perfectly correct all the errors introduced by this channel epsilon. So the proof is very simple. So now we construct a projector PA, which is a projector of all this, like all these code spaces. For example, here, this group EA, epsilon A, this will take this code space here and here. So conjugate union of these two. So PA will map the here and here. It's a projector on this union of these subspaces. And if you consider this recovery RA, where this lambda is introduced to make things trace non-increasing so that everything is physical, then if you calculate this quantity, this term, you will get your state back. So psi L, you will get the state back, but with an extra factor, and this is the probability of success. So now with this thing, we introduce our 3 qubit code, which is like we encode the 0L in a permutation invariant state, 100, 010, and 001, and 1L as 111. And so we define these projectors, and so we divide our amplitude damping noise channel based on their damping strength. So there will be two types of damping. First is there is no damping when this A0, 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 and there are three first order damping. There are 3 Krauss operators, A100, 010, and 001. So we construct these 3 projectors, P0, which is the projector on the code space, and P1 is the projector on the error subspace introduced by this first order damping, and PF is just to make things complete. And so this, if we just do a projection P0 and P1, and if we get some satisfactory outcome, we can say that we can distinguish if there is 0 order damping, if there is no damping, or there is first order damping, and accordingly we apply these recoveries. So we can we can construct a recovery channel. This is trace non-increasing recovery channel, R0 P0 and R1 P1. And if we apply this recovery channel, we get an entanglement fidelity for the 3 qubit code to be 1 minus 0.5 gamma square. So there is no linear term gamma. That means we have corrected all the single qubit errors. So if you compare the performance of the 3 qubit code with the existing codes in the literature, so we see that the 3 qubit code outperforms all these codes, like this 4-1 long code or the 5-1-3 perfect code, 7-1-3 Steen code. But given that you are paying in terms of probability, your recovery is not deterministic, but you are gaining a lot in terms of fidelity. So what is the probability of success? So if you, this now probability of success depends on what encoding you are doing, what is your information. So if you are encoding one single qubit, and any encoded state can be written in this general form. So the probability of success is basically this term if you encode. So there is no phi dependence, this only depends on theta. And if you plot for theta equal to pi, the probability is maximum, and for theta equal to 0, the probability is minimum. And we can see even if the gamma is 0.2, which is pretty high, still you are successful more than 65%. So its probability of success is pretty good. So after this 3-1 code, we introduce a family of AD codes which satisfies our error correction condition. And we encode, so this is the permutation invariant state, we denote it as this NE, and we encode our logical states in this. So these are our code words. So to encode k qubits and protect AD errors up to order t, we need at least 2 to the power k t plus 1 minus 1. This many qubits we need to protect, to encode k qubits and protect it from t order errors. So when k equal to 1, t equal to 2, so n should be 5 here, and this is the 5 qubit code. And this can correct up to second order. So the fidelity expression, there will be no gamma squared term as well. So to prove that to prove the optimality, we introduce a noise adapted Hamming bound. I know everyone is familiar with Hamming bound, so it gives a bound on the minimum resource you need to do error correction. So if you have a system for, like, you are encoding n qubits of dimension qp to k logical qubits of dimension ql, so, and you want to correct t order of amplitude damping, so this is the inequality that will give you the bound for the minimum resource you want. For qubit case, we just put qp equal to ql equal to 2, and it boils down to this simple expression. So we have already introduced this 2 to the power k t plus 1 minus 1 k family of codes, and we claim that it saturates the Hamming, this noise adapted Hamming bound when k equal to 1. So if you put k equal to 1, it comes down to 2t plus 1 comma 1 code. And as you have seen in the last slide, this is the noise adapted Hamming bound. So if you put it here, so we have to prove this. And this can be easily proved. You just take this 1 plus x to the power n with this expression and substitute n with 2t plus 1 and x to be 1. And this proves the optimality when k equal to 1. So as a summary, we demonstrated a new framework for quantum error correction that can perfectly correct all the errors, but with a certain probability. The probability will be deterministic, will not be deterministic. So we demonstrate the shortest possible quantum code for amplitude damping noise, a 3-qubit code, which was not reported earlier in the literature. And we propose a new family of 2 to the power k t plus 1 minus 1 k codes to encode k qubits, and it can be, it is optimal for k equal to 1. And we also give a noise adapted Hamming bound for amplitude damping noise. Yeah, so this is, again, we show that k equal to 1, it is optimal, and then our code outperforms most of the state-of-the-art codes in terms of fidelity, given that you are compromising on probability of success. And the resource is also fewer. Yeah, thank you.
So if there is no question, so let's thanks Sourav and the other speakers of the session.